Okay. Any questions? So what we had done yesterday was mainly we said that, okay, we were looking at the probabilities which were proportional to what we call the omega, which is the number of microstates corresponding to a given macrostate. And we define the entropy as the Boltzmann constant times logarithm of this omega. So once we can calculate entropy, all the other thermodynamic properties we can derive. And now as an example, we were looking at the ideal gas. Now, quantum mechanics tells us that we can treat this ideal gas as a particle in a box. In this example, let's assume a cube of side length L. The energies of individual particles, of each particle, we can write as h bar squared over 2m times pi squared over L squared nx squared plus ny squared plus nz squared. So the total energy of the system will be just the sum of these. L squared is nothing but v to the power 2/3 nxi squared plus nyi squared plus nzi squared. And so one thing we said that from this, the number of states is basically the integers nxi, nyi, nzi. How many such integers can we find such that this equality holds? So that will give us omega. But you see that those number of states is not really just a function of E, but rather omega is a function of, well, n, of course, but E times v to the power 2/3. So this is our omega. And then we said that we had already derived that since this is true, PV should be equal to 3/2 PV should be equal to the energy. Furthermore, another thing that we can read straight away from this observation is that entropy, which we had defined as logarithm of omega, is itself a function of n and E times v to the 2/3. So if we have an adiabatic process, S is constant, which basically tells us that E times v to the 2/3 should be constant in this process. And since we already know that E is just equal to PV up to this constant 3/2, so we see that PV to the 5/3 is constant in an adiabatic process. So this was just an equation that we had derived for the ideal gas using also thermodynamics. So we could obtain exactly the same relationships using this statistical approach. Now let's try to calculate this omega explicitly. Now this is the equation that we will have. We are basically asking how many solutions does this equation have? Or let's write it in a slightly different form. Sum over I nxi squared plus nyi squared plus nzi squared. This should be equal to E times v to the 2/3 times 2m over h bar squared pi squared, let's just call it epsilon. So how many solutions does this have for integer nx, ny, and nz? Now to see how we can find these integers, let's look at a simple case. How many solutions does n squared plus nx squared plus ny squared is equal to, let's say, epsilon has? A simple. I mean, in the previous case, in the actual case, we should find 3 n integers. not just 2, but let's just, as a toy example, let's try to determine how many solutions does this add. Now, you see, let's just imagine this 2-dimensional space. Since we already know that nx and ny, they should be 1, 2, 3, etc. So let's say the horizontal axis is nx, the vertical axis is ny. Now, I just draw the first quadrant because that's the quadrant we are interested in. So the points that we are actually interested in, let me put the numbers 1, 2, 3, 4, 5, 1, 2, 3, 4, etc. So there's a possible point over here, another one over here. So they form a lattice. Of course, for the time being, I didn't impose the energy constraint. From this simple example, we can see a couple of issues. One thing is for most values of epsilon, there are actually no integer solutions. You see, if you say epsilon is equal to 1.5, no solution. Epsilon itself has to be an integer. Otherwise, there is no solution. And not even for all integers, there is a solution. But then keep in mind that eventually we will be dealing with macroscopic systems where n is huge. In such a case, well, you see, in this 2-dimensional example, the problem is the energy levels are discrete and the spacing is large. But when you go to macroscopic systems, the energy spacing will be negligible. The possible values of energy will be almost continuous, almost. Still, the exact value will be somehow quite irregular. But then there is another issue. I mean, at least in this problem, we are saying that we are isolating the system. Well, no system is completely isolated. Energy always has some fluctuations. So what we will be really interested in is the number of states within an energy range. Let's say E minus delta over 2 and E plus delta over 2. Where delta will typically go as 1 over the square root of n. So eventually it will go to 0. Now, so keeping these in mind, what we will first do is not just straight away calculate the number of states having a given energy, but let's define another function, sigma E. This is the number of microstates having energy less than E. If we can calculate this, omega will be nothing but sigma epsilon plus delta over 2 minus sigma epsilon minus delta over 2, or d sigma by d epsilon dE times delta. This will be our omega. So once we can calculate the sigma, we can obtain omega. Now, how to calculate these omega? You see, this equation on this 2-dimensional example, it defines a circle. Or if I just say less than or equal to, it defines a disk. And since nx and ny are larger than 0, I'm interested in the number of points, let's say, within within this area. I'm interested in how many points are there in this 1/4 of a disk. Well, see, the easiest one would be, since these separations are 1, I can imagine these areas around these dots This is a unit area. There is another unit area over here, another one over here. Another one over there. Then the question is kind of modified. How many such unit areas can we find in our disk? Now that's kind of an easier question to answer, because basically since each one of these unit areas have area 1, if we calculate the total area of my disk, then I know how many unit areas are there, approximately. Of course, there will be errors in my calculation. The errors will be proportional to the circumference. You see, there along this circumference, the number of unit areas that intersect that circumference is, how does it scale with n? Well, in our actual example, we are interested in a 3-dimensional number space, and the radius of this disk is proportional to, if you go back to our actual example, the radius of my disk is proportional to this number, e times v to the power 2/3. Well, the surface area is proportional to this number to the 3n minus first power. Number of unit squares inside the disk, on the other hand, would scale as the radius to the power 3n. Now, if you take the ratio would scale as 1 over e times v to the 2/3, which is basically 1 over n. Yeah, larger than n. E scales as n, v to the 2/3 scales as n to the 2/3. So it's actually the error introduced due to this boundary over here goes as 1 over n, and eventually we can just ignore it. That will be negligible. So for us, it will be enough to just calculate, well, in this 2-dimensional example, this area. Well, the area is just pi epsilon squared. So in our case, sigma e will be pi epsilon squared. This is the total area divided by 4. So we are done in this 2-dimensional example. Well, of course, now we need to do the 3n-dimensional example. So this is our constraint. So we are trying to find the number of integers the number of sets of integers that satisfy this relation. So this is a 3n-dimensional. Well, this is the sigma e is equal to the volume of the 3n-dimensional sphere of radius square root of epsilon. So this is what we need to calculate. So this is equal to the 3n within my sphere. Let me just call this R. So here the notation is d3n is equal to dnx1, dny1, dnz1, etc. Absolute value of n is, or let's say square, is nx1 squared plus ny1 squared plus nz1 squared plus nx2 squared plus etc. Well, the easiest way to calculate this integral will be just go to spherical coordinates. This is dn, integral over the magnitude, times n to the power 3n minus 1 times the omega 3n dimensional solid angle. N goes from 0 to r. So sigma e is actually r to the power 3n divided by 3n times d omega 3n. Now we already know how sigma depends on energy, at least. Energy and volume, because the only thing that we don't yet know is that the total solid angle, and that total solid angle basically depends on the number dimensions of the space only. So it depends on n only. So now we need to calculate that one also. Any ideas, any suggestions? Well, we can try to extract the total solid angle from an integral that we already know. Let's try to calculate the solid angle. By the way, let me also divide this by 1 over 2 to the n. Because I'm not looking at the total volume. I'm just looking at the first quadrant. Because n's, they are all positive. Let us look at an integral that we already know. Overall space. We already know the value of this integral because this is nothing but 3n Gaussian integrals. Each Gaussian integral would give me a square root of pi. And there are 3n of them. Well, I can also try to evaluate exactly the same integral by going to spherical coordinates. In spherical coordinates, that integral becomes the n to the 3n minus 1 from 0 to infinity, the omega 3n e to the power minus n squared. This is equal to, well, this solid angle integral is independent of n, small n. From 0 to infinity, the n to the power 3n minus 1 e to the power minus n squared. This should be equal to square root of pi to the power 3n. So the solid angle that I'm interested in is just pi to the power 3n over 2 divided by this one-dimensional integral. Now let's try to evaluate that one-dimensional integral. Well, let me just make a change of variable. Let me say n is equal to square root of x. Then it will just become a gamma function. dn is equal to dx over 2 square root of x. So 0 to infinity dn, n to the power 3n minus 1, e to the power minus n squared becomes, from 0 to infinity, dx over 2 square root of x, n is just x to the 3n minus 1 over 2, e to the power minus x, which is 1 over 2 gamma 3n over 2. So we are practically done. Is equal to pi to the power 3n over 2 times 2 divided by gamma 3n over 2. So we were looking at sigma. Now we know what sigma is. R to the power 3n divided by 3n 1 over 2 to the power n minus 1 pi to the power 3n over 2 divided by gamma 3n over 2. Or let me not write it that way. Let me just now let me also substitute what R was. This is R squared. So sigma of E is equal to E times V to the 2/3, 2m divided by h bar squared pi squared to the power 3n over 2, pi to the 3n over 2 divided by 2 to the n times gamma 3n over 2 plus 1. So if I make some cancellations, this will cancel this one. Now let me just keep it there. So this is our sigma. Well, now we need omega. But we already said that omega is just derivative of sigma with respect to E multiplied by this uncertainty in the energy of my system. So this is 3n over 2 e to the power 3n over 2 minus 1 v to the 2/3 2m, here I have 3n over 2 divided by h bar squared pi 1 over 2 to the n gamma 3n over 2 times delta. Now we can just write the entropy.
You also have 3n over 2 factor, right?
Now you see, there is this gamma 3n over 2 plus 1. I cancel the 3n over 2. Logarithm of E and plus 3n over 2 logarithm of v to the 2/3 2m divided by h bar squared pi minus n logarithm of 2 minus logarithm of gamma 3n over 2 plus logarithm of delta. Now let's remember some numbers. You see, we said that n is typically of the order of 10 to the power 23. If you look at over here, the first term is 10 to the power 23 minus 1. Just ignore it. And we said that delta is typically 1 over square root of n, 10 to the power minus 10, let's say, or 11. So logarithm of delta is typically minus 11. You see, this is minus 11. Let's say 10. Around that, the magnitude is around that number. Here we have n, 10 to the power 23. Again, this is just negligible. Well, this basically tells me that whichever value you choose for delta, it doesn't really change what omega is. It doesn't change what the entropy is. Well, that's again because of this, the property of huge numbers. You see, when you talk about the volume of a system, the volume is basically you just sum the areas of the concentric shells, let's say, in a sense. The outermost shell is so enormously huge compared to just the next shell. If the dimension is huge, you just can ignore the volume of the inner shells. The total volume is determined by the outer shell. Now, there are still some simplifications we need to calculate. So, what about this one? What is that number? Logarithm of 3n over 2, let's say minus 1 factorial. Now, we have what's called Stirling's approximation for the factorials. Now, if you have a huge number n factorial, the logarithm of this one is just sum of I from 1 to infinity, 1 to n of logarithm of I. This is I, this is the logarithm of I. So logarithm 1 is 0, logarithm 2 is, let's say, somewhere over here, logarithm 3 is somewhere over here, this is logarithm 4, logarithm 5, logarithm 6. So this is more or less how the logarithm function changes. It increases all the time, but its rate of increase gets smaller and smaller. Now, so this basically tells me that I can approximate this by the integral of logarithm of x dx from 1 to n. You see, this integral you can this integral will be basically the area below this curve. Now, logarithm 1 is 0. It's the area of this line. Logarithm 2 is the area of this rectangle. Logarithm 3 is the area of this one. Logarithm 4 is this area over here. Logarithm 5 is this one. So you see, the sum of the areas below these, in these red rectangles, the sum is more or less equal to the area below that smooth curve. The area below that smooth curve is nothing but that integral. And in fact, that area, the integral from 1 to n should be a lower bound of my sum, and the integral from 1 to n plus 1 is an upper bound to my sum. But, I mean, the integral up to n or n plus 1 doesn't really make a difference if n is of the order of 10 to the power 23. So basically I can just approximate it by this number. And this integral, if we just evaluate the integral, it is just n logarithm of n minus n. Again, I'm just ignoring some factoring of 1 because I know that n is a huge number. So now we have everything. So S is 3n over 2 logarithm of e plus 3n over 2 logarithm of v to the 2/3 times 2m over h bar squared pi minus n logarithm of 2 minus 3n over 2 logarithm of 3n over 2 plus 3n over 2. This is the entropy we have. Or let me just combine some of the terms. Logarithm of e times v to the 2/3. Well, let me separate the v. Times 2m over h bar squared pi. Times e, the base of the natural logarithm, divided by 3n over 2, 1 over 2 to the 2/3, plus n times logarithm of v. And from this expression, basically, we can derive everything. You see, if you remember our thermodynamic relationship, the first law of thermodynamics written in this form, 1 over T dE plus P over T dV minus mu over T dN. So the temperature of this system is the derivative of entropy with respect to energy, keeping V and N constant. This is the derivative with respect to energy of 3n over 2 logarithm of E plus other terms which don't depend on E. And hence 1 over T is equal to 3n over 2E. Or, okay, sorry, their entropy has a factor K over here. Or E is equal to 3n over 2 KT. Something that we had already discussed several times. Now the pressure, P over T, is just the derivative of entropy with respect to volume at constant energy and the number of particles. This is equal to derivative with respect to volume of, now if you look at our expression, nk logarithm of V plus other terms which are independent of V at constant E and N. So this is nk over V. So we obtain PV is equal to nkt. If you look at this expression of S, it is already you see that S is a function of E times V to the 2/3 and N. So we see straight away that in an adiabatic process, adiabatic reversible process, E times V to the 2/3 is constant. So we just read everything. I'm not calculating mu on purpose. We will discuss it later on. Any questions up to this point? Let's look at a paradox. Okay, everything looks great. Now let's look at this expression. S is 3n over 2 k times logarithm of E over n plus n times logarithm of v. There's E over n times k times logarithm of v over here plus n times, let me just put c. Independent of E, N, and V. It just depends on the mass, some constants like pi, h bar, etc. But it doesn't depend on E, N, and V. Well, some of the properties that we were expecting from entropy was one of this is S should be extensive. Now, what does it mean to be extensive? So, for example, we expect E should be extensive. Well, why? What does it mean? If you have two, let's say you have one system which has an energy E. Then you bring another identical system. It will also have an energy E. If you combine the system size has been doubled. So its energy is doubled. Its volume is doubled. So these two, energy and volume, are extensive properties. Its temperature is the same. Its pressure didn't change. So these are what we call intensive properties. The number of particles have been doubled. If the system is doubled, all these properties should be doubled. Temperature, pressure, chemical potential. These are intensive properties. Well, why do we expect the entropy to be an extensive property? Let's see. Let's assume we have these two systems. Identical. And remember how we define the entropy. Delta S is just Q over T. Now, if I double the system, let's see, I also double the energy that I give to my system. If I'm doing the same thing to both systems, let's say Q is given here, Q is given here. The entropy of the combined system, the change in the entropy of the combined system, is, well, 2Q over T, which is Q over T plus Q over T, which is the change in the entropy of the first system plus the change in the entropy of the second system. At least the changes are extensive. And hence the entropy should be an extensive property. But if you look at our system, you see, if I change my system, if I double my system, I have one system, the second system, identical systems. The energy will be doubled, the number of particles will be doubled, this ratio doesn't change. But there's a n in front, so this is doubled, so this term is doubled. This term is also doubled because there's an n over here which is doubled if I duplicate my system. C doesn't depend on E or N or on the size of my system. So this term is doubled. Well, if I look at this term, n is doubled, but V is also doubled. So this term, if I just duplicate my system, take two identical systems, this term doesn't become twice the value for one system. Now, why is this a problem? Now, let me look at an example. Okay, one reason why it's not a problem is that it just makes entropy a non-extensive property, which shouldn't be. Let me take two gases. Divide them by a compartment. Here on the left-hand side, I have N1 molecules of gas, one in a volume V1, and they have an energy E1. On the right-hand side, I have N2 particles in a volume V2, energy E2. And they are separated at first. Well, the total entropy of that entropy of the system will be, let me just copy this expression. Now this is the entropy. The total entropy of the combined system will be 3n1 over 2 k times logarithm of E1 over n1 plus n1 times logarithm of V plus n1 times C1 plus 3n2 over 2 k times logarithm of E2 over n2 plus n2 logarithm of V2 plus n2 of C2. This is initially. Then let's assume that I remove that barrier, and then the gases basically mix. Afterwards, okay, I have N1 particles having energy E1 and the total number N1, but now they are distributed over a volume V1 plus V2. And then I have N2 particles of type 2. They have an total energy E2, but they are distributed over a volume V1 plus V2. This is the total entropy after I remove the barrier. Now, how much did the entropy of the system change? Well, these 3 and 1 over 2k logarithm with etc., they are cancelled in the ratio. what will remain in the ratio is n1 times logarithm of v1 plus v2 plus n2 times logarithm of v1 plus v2 minus n1 times logarithm of v1 minus n2 times logarithm of v2. This is what is called the entropy of mixing. Well, this is not really a big surprise. If you have two different gases, let's say, and you have an isolated system, you just remove the barrier, then they start mixing on their own. Well, the second law of thermodynamics tells us that if there is a process going on spontaneously in an isolated system, entropy can stay the same or it can increase. This tells me that this process is not a reversible process if these two particles are different, which basically tells me that the entropy should increase, it cannot stay the same. It's not reversible because just putting back the barrier will not bring the system back to its initial configuration. So if you mix two systems, entropy increases. It's not a big surprise. But the problem is, what happens if the two compartments have exactly the same, are made up of the same gas? You basically have the same gas, the same temperature, etc. They're identical. You remove the compartment, nothing changes. You put back the compartment, nothing changes. So in such a case, the entropy should not increase. But according to our expression of the entropy, there is an increase in the entropy, which shouldn't be there. That's the problem that we should address. So what's it that we did wrong? What did we miss? You see, the expression we had, it seemed to reproduce everything we know about the ideal gas. But then we have this problem. Well, I mean, if you don't mind, let's just continue for half an hour more and then we can end the lecture today. Now, let us look at this problem in a slightly different context, in a slightly different form. Let me rewrite this change in the entropy in this form. N1 times logarithm of V1 plus V2 over N1 plus N2 plus N1 times logarithm of N1 plus N2 plus N2 times logarithm of V1 plus V2 over N1 plus N2 plus N2 times logarithm of N1 plus N2 minus N1 times logarithm of V1 over N1 plus N1 times logarithm of N1 minus N2 times logarithm of V2 over N2 plus N2 times logarithm of N2. Well, I just added and subtracted these second terms in each line. Now, the reason why I did that is if, you see, the problematic case was if both parts were identical. meaning that they have identical the same gas, the same type of gas, at same density, at same temperature, etc. So that basically means that V1 over N1 should be equal to V2 over N2. This should be equal to V1 plus V2 over N1 plus N2. But this tells me that this term will be cancelled by this one will be cancelled by this one. So in this special case, delta S is just N1 plus N2 logarithm of N1 plus N2 minus N1 times logarithm of N1 minus N2 times logarithm of N2. Or let me even rewrite this term. N1 plus N2 logarithm of N1 plus N2 minus N1 plus N2 minus N1 logarithm of N1 minus N1 minus N2 logarithm of N2 minus N2. You see this minus N1 minus N2 and this minus N1 plus N2, they cancel each other.
Why do we have minus sign over there?
Yes.
Plus all.
Oh, plus, all of them are plus, yes. Let us see if that is correct. My mistake is over here. This is minus. So this is all minus. No, sorry. No, these are pluses. This is minus, this is also minus. So these are also minuses. But then this tells me, you see, the delta S that we are writing is actually the final entropy of N1 plus N2 particles minus the entropy of S1 particles minus the entropy of N2 particles. Since we are looking at this special case where both compartments carry identical systems at identical at the same conditions. And this difference turns out to be, you see, if you look at this combination, this is nothing but the logarithm of N1 plus N2 factorial. This combination is logarithm of N1 factorial. This is logarithm of N2 factorial by Stirling's approximation. So this is equal to logarithm of N1 plus N2 factorial minus logarithm of N1 factorial minus logarithm of N2 factorial. So basically, we can write it in this form: S of N1 plus N2 number particles minus logarithm of N1 plus N2 factorial minus entropy of N1 particles minus the logarithm of N1 factorial minus entropy of N2 particles minus the logarithm of N2 factorial. So this basically tells me that this is zero. The problem of the mixing of identical particles can be corrected if we replace the entropy of n particles by the entropy of n particles minus the logarithm of n factorial. Or omega should be replaced by, let's say, the corrected omega. Let me put the initial current omega. This by setting the corrected omega by omega 0 divided by n factorial. Then the problem is solved. But then the question is, why n factorial? Why do we divide by n factorial? Remember, n is the number of particles we have. Well, the answer is given by quantum mechanics. The particles are indistinguishable, at least some of them. And remember, this problem arises when we have the same particles on both compartments. Now, how does this solve the issue? You see, what we have done in the calculation is, let's say I have one particle over here, another particle over here, and I said that if this has the quantum numbers nx1, ny1, and z1, the other one has particles, quantum numbers nx2, ny2, and nz2. And this was one state, one microstate. So this is particle 1, this is particle 2. And now we have another state. I say here I have particle 1, and here I have particle 2. Now particle 1 has the quantum numbers nx2, ny2, and z2. And particle 2 has the quantum numbers nx1, ny1, and z1. This is another state. That is, classically we can separate these particles. So, or if these two particles are different particles, we can just, these two microstates correspond to different microstates. These two configurations correspond to two different microstates, so we should count them as two. But if these two particles are identical and indistinguishable, we cannot really say which one is in which state. So these two configurations are in fact one microstate. So that's basically the mistake we did in our counting. If there are, let's say, n identical particles, then we can assign these quantum numbers to these identical particles in n factorial different ways. Well, this is also not completely correct. You see, for each particle we are assigning basically 3 integers. If all these triplets are different from each other, then this is correct. That is, all of the particles are in different states. But if, let's say, 2 of them are identical, then just changing their position doesn't give me really a different assignment. So I should actually divide this by n1 factorial, n2 factorial, etc. And let's say m factorial, such that n1 plus n2 plus nm is equal to n. And what it means is, let's say there are n1 identical triplet nx, ny, nz for the microstate. And there are N2 identical triplet, different than the previous one, of course. So basically what, now the problem over here is, for a given energy, a given macro state, there are many microstates. And for each one of these microstates, the numbers N1, N2, and Nm can be different. So it's not so easy to take them into account, at least within this approach. Later on we will do that. But within this approach, we cannot really take that easily into account. What the thing that Gibbs has had done is just, instead of this N1 factorial, N2 factorial, Nm factorial, he just put 1. So there's just n factorial, so he divided by the n factorial to get rid of the multiplicities. Well, this will be correct if the probability of having two particles, the probability that of two particles having the same quantum numbers is negligible. So if in a corresponding to a given quantum number, the probability of having more than one particle is negligible, the approximation of Gibbs is correct. And we will see that this, for example, corresponds to if we have the energy is high. If the energy is high, well, probably there will be a huge number of available microstates for in each particle, and the probability that both two of them will have the same quantum numbers will be negligible in that case. But we will see later on in cases where this is not correct, where the energy is low or the temperature is low, it will be important. So we need to take those factors into account. And then we will see that there are actually two different kinds of particles that we call fermions and bosons. Now, for bosons, there's no problem of having more than one particle in the same quantum state. For fermions, they would avoid that. And this behavior will cause them to behave differently at low temperatures. Well, at high temperatures, they behave similarly. They just approach this description, this classical description, let's say. But at low temperatures, they will behave completely differently. Any questions?
Does the entropy change if we remove the compartment between the different parts of the gases?
Yeah, you see.
You said that it should be zero, the entropy change, right?
In the case, if the left-hand side has temperature T, the right-hand side has temperature T. If the left-hand side has the density N, right-hand side has the density N. Left-hand side has the pressure P, right-hand side has the pressure P. And they are made up of identical particles. Then, if I remove the compartment, nothing should change, because nothing changes. If I replace the compartment, I just get my initial configuration.
Yeah, but in this case, you should have identical particles.
Yes.
Otherwise, particles may interchange it.
Otherwise, entropy will increase, and the increase will be given by this entropy of mixing that we have calculated. This will be the entropy of mixing if you have two different particles on both compartments. But if they are identical, they are at the identical configuration, identical temperature, identical pressure, etc. If you remove the compartment and replace it, you get your initial configuration, so entropy shouldn't increase.
Can we say for any two particles, can we say that they are identical? In reality, not in theory.
Well, as far as we know, two electrons are always identical. Two oxygen atoms are identical.
But we can label them, right?
No, you cannot.
We can.
Classically, you can. You can follow their trajectory, but quantum mechanically you cannot. If you try to follow their trajectory,
yeah, I know.
that means you know the momentum. That's not possible. You see, that was kind of well, the problem arises in you see, in this problem, although we started from the quantum mechanical description of the quantized energy levels, you can actually do exactly the same treatment just using classical arguments. And you will still obtain the same paradox. So kind of this concept of identical particles, you can discover it even without quantum mechanics, just to solve this problem. That's what Gibbs did.
No, I was just asking my question classically.
Well, classically what you can do is you can just label the particles based on their trajectories. So you can just give them some labels initially and follow their trajectory. So they will carry their labels with them. So classically you can distinguish them. But quantum mechanically there's no way to do that because you cannot follow their trajectory. So there's no way to distinguish them. I mean, you see, quantum mechanical is at a given time you label the particles. When you detect one of them over here, since you are not able to follow them, you don't know which one it is. So you cannot give it a label afterwards, even if you would label them at a given time.
So you're losing the information, right? Can we say such a thing, that we are losing the information?
Well, you see, you are losing the information you never really had. So when you say you are losing the information, you get the impression that you actually had that information. You see, classically you can give them labels, but even classically, on the practical sense, you cannot really follow them. So in that sense, even classically, if the world would be classical, you don't really have that information on practical terms. But in that case, ideally, you could do that. And hence, ideally, they would be distinguishable. And hence, no n factorial. Okay, so see you next week. I will try to prepare some assignments for this weekend. So just check out the class. You will probably be getting emails.